All right, good afternoon, everyone. This is Joe Steele from LIFT, Lightweight Innovations for Tomorrow here in Detroit. I want to welcome you to the April 2018 Lift Off webinar series featuring the Aluminum Extruders Council, discussing extrusion technology and how it is supporting the auto industry and other industries going forward. The Lift Off webinar series is brought to you by LIFT, along with the center, the Michigan Manufacturing Technology Center, are the manufacturing extension partnership here in Michigan. We'll learn more about them in just a second. But I wanted to welcome you and provide a couple of housekeeping items before we get going. Please put your phone on mute if you haven't already. That will allow the presentation to go on without too much background noise, and we'll be recording it, as I mentioned. So you can go back and listen to it again later, or share with your friends and family. They were unable to join, and they won't hear that noise in the background as well. Also, if you do have questions, please use the chat function that is on your screen, the GoToMeeting chat function. You can address the question to the organizer. That will come to me, and we'll facilitate the Q&A afterwards. So a little bit about LIFT. We are based here in Detroit, as I mentioned. We are one of 14 Manufacturing USA institutes. We are sponsored in part by the Department of Defense, and our mission is to accelerate the development and application of innovative lightweight metal production and manufacturing technologies to benefit both the U.S. commercial and defense markets. We really do that in three ways. There's three buckets. The first is technology development. We have a series of projects going on, taking a look at lightweighting and lightweight metal technologies. You can find out more about those projects at lift.technology, or following us on Twitter at News from LIFT, or visiting our website at lift.technology, or giving us a call at the phone number you see on your screen. We also focus on that technology transition. If there's innovations taking place in the market, we want to make sure that those innovations actually find their way into industry and don't end up just sitting on the shelf somewhere. We also have a number of education workforce development initiatives that we have invested in. That is the third leg of our stool, because as industry know and have heard, there are plenty of manufacturing and advanced manufacturing jobs available, and not enough bodies to fill them in some instances. So we want to make sure that we are opening the eyes of students to the world of advanced manufacturing. We also want to make sure that we are providing training opportunities to those workers who may be changing careers, or maybe in the career in advanced manufacturing, but need to have some advanced to have some additional skills and additional training as well. As I mentioned, we are here in Detroit. Just last year on Manufacturing Day in October, we cut the ribbon on our 87,000 square foot high bay facility, which includes some of the machinery that you will see on your screen. We also provide a number of the services that you see on your screen as well. We are jointly located here in Detroit with IACME, the Composites Institute. They are another Manufacturing USA institute. They're based in Tennessee, but they have their automobile scale-up research facility here with us in Detroit. So we tackle both the metal world as well as the composite world here in our facility in Corktown. So please check us out at lift.technology and visit IACME, or come visit us here on Rosa Parks Boulevard in Detroit. As I mentioned, the Lift Off webinar series is brought to you by LIFT and the Center. So I want to give the Center a chance to talk about their services and the support they provide manufacturers across the state of Michigan. So I believe we have Elliot Forsyth on from the Center to do just that. So Elliot, I will hand it off to you.
Great, thanks, Joe. Can you hear me okay? Joe?
We can.
Great, thank you. Thank you, everyone, for joining. I hope you've been taking advantage of these monthly lift off events. So as Joe pointed out earlier, we are one of 51 organizations across the United States, including Puerto Rico, who are fundamentally given the mission to support small to mid-sized manufacturers to help them prosper and thrive. As you can see on the screen, the host of services that we provide span everywhere from Industry 4.0, accelerating technology, operational excellence, cybersecurity, and you know, we take great deal of pride in the number of organizations that we've helped to transform and to make substantially more viable. To that end, we survey our clients once every quarter. We ask them through a third-party confidential service to rate our performance and demonstrate the economic value that we create for them. And their data suggests that for every dollar that they invest with us, they get $106 back in return, either in terms of new sales or cost savings. So we're very proud to be part of that. We've been in business for 26 years, and so have a deep history. Almost a year ago, or a little bit more than a year ago, because of our long-standing partnership with LIFT, we were given the opportunity to embed a very talented engineer to help support LIFT and to connect small to mid-sized manufacturers into the wonderful technology that's emerging out of LIFT. So on the line as well is Greg Peterson, who's that engineer. And we have enjoyed a very, very deep relationship, not only with LIFT, but from the speaker who you'll be hearing from today, from the Aluminum Extruders Council. Wonderful work that this organization is doing. Thank you.
Well, thank you. And today's presentation is to better understand and review the rationale for specifying microstructure and the critical variables to consider. We will examine how such specifications can be achieved by optimizing geometry, chemistry, quench, and aging. We will also review a case study with these considerations applied. I'm Mark Butterfield, Chairman of the AEC Automotive Team Market Team and Managing Director of Magnode Corporation. First, before we start, just a little bit about the AEC and Magnode. The AEC is the Aluminum Extruders Council, the Industry Association for North American Extruders. We represent approximately 60 extruder members, accounting for approximately 75% of all North American extrusion production. And our teams are focused on user education, member excellence, fair trade, and as we are here today, the automotive industry. Since 2014, approximately 110 million pounds of auto capacity has been added, and approximately 150 plus in the pipeline as far as capacity goes to support the automotive industry. Magnode, a Shape Corp company, has been a long-term AEC member with heavily involvement within the communities of AEC, with extrusion and fabrication operations in Ohio. Magnode, a leading supplier of highly engineered custom extrusions and fabricated components for the automotive and other precision applications. So when we talk about specifying extrusion, we ask the first question, what do you want? And we see this as we receive inquiries relative to extrusions and different applications. And we always ask the question, what is it that you're looking for? Is it an alloy? Most likely not. Is it a temper? Most likely not. The interest is in the properties and the microstructures required in order to meet the specifications and the performance needs of the application. So we're going to focus in on properties and microstructure, which as a result of these needs lead us to the alloy and temper. So the next step is specifying and achieving. Extrusion properties and performance is driven by geometry, chemistry, and microstructure processing. Extrusion properties and performance is achieved by raw material structure, or raw material in the form of a billet, the extrusion process and tool design / metal flow, which occurs within the die and extrusion press, and the quench and aging process associated with the final product. In today's webinar, we'll go through each of these items to bring some clarity around the achievement of microstructure. In regards to geometry, component geometry can often offset alloy limitations. So this is an example of a Lotus Evora where 6060 profile or alloy was utilized in many profiles. Now the benefit to this was tighter tolerances, more efficient cost, and better downstream manufacturability. So in this case here, the chassis tub, we utilized 20 profiles of 6060. Unusual to utilize that alloy in this application. And here, the front subframe, 6060 was also utilized in eight profiles. Again, the advantage is tighter tolerance as a result of the quench associated with a 6060 alloy, higher productivity, which results in a lower cost, and better downstream manufacturability. This was all achieved by the use of geometry. Lotus used profile geometry to offset the lower strength of the preferred 6060 alloy. So the profiles that are shown here today in today's industry are probably what I would consider moderate in complexity. Extruders today can produce more complex, greater numbers of hollow profiles, which allow in the design and application, and it can allow you to utilize a 6060 or 6063 alloy, where maybe in some applications with a simpler geometry may require a higher strength 6082 alloy. So profile geometry should always be taken into consideration in combination with the alloy itself. So chemistry. This is a different alloy chemistries yield varying mechanical properties for the resultant extrusion. So this chart basically shows the alloy series as well as the major alloying element for each. So we have the 1000 series, which is minimum 99% aluminum as far as alloying elements. 2000 series, which is copper, which provides the high strength, relatively low corrosion resistance, excellent machinability, and heat treatable. 3000 series, which is manganese, low to medium strength, good corrosion resistance, poor machinability, but good workability, primarily in impact extrusions, impact applications. 4000 series, which is silicon, not available as extruded products. 5000 series, which is magnesium, low to moderate strength, excellent marine corrosion resistance, and very good weldability. Then 6000 series, the most dominant in the extrusion industry, which is magnesium and silicon. And again, most popular extrusion alloy class. Provides good strength, good corrosion resistance, good machinability, good weldability, good formability, and is a heat treatable alloy. 7000 series, which is the primary alloying element of zinc, is very high strength, but poor corrosion resistance, good machinability, and again, another heat treatable alloy. When we look at the different alloys, this is an example of some of the specific alloys within the 6000 series. This is a broad spectrum, the 60-60-63, lower mag silicon alloy all the way up to a 6082, which is a higher strength, and a 7003 in two different tempers. This represents the temper to that specific alloy, as well as the yield strength, ultimate strength, and percent elongation. These are minimum requirements relative to these alloys. Trace amounts matter in regards to chemistry. So here's an example of a 6063 alloy and a 6061 alloy. And we can see the total alloying elements are represented by less than 3% relative to percent aluminum. So as we saw in the prior slide, the difference in mechanical properties between a 6063 and a 6061. But this represents what minimal difference there may be in a specific alloy. So for example, your irons, your copper, your manganese, the magnesium, zinc, titanium. So trace amounts matter. As of June 2016, there were 537 alloys registered with the Aluminum Association. And this is a key note. That does not include proprietary alloy variants. And that's considerable. So you can see here in the 6000 series, there is 102 at that time. And the purpose for that is the ability to tweak an alloy and tweak a chemistry specific to the needs that are required for the application, whether that be grain structure, performance, mechanical properties. But as of 2016, 102 within 6000 series, 83 within 7000 series, and 42 within 3000 series. Again, does not include proprietary alloys specific to an application. Here's just a brief primer in regards to alloy. Any one alloy can have a variety of formulas and hence can be tweaked to optimize properties. So what we're looking at here is a graph that shows the silicon content represented in the vertical axis and the magnesium content represented in the horizontal axis. So the lower silicon mag content represented by a 6060 is typically used in the auto trim, heat sinks, electronic housings. However, we saw in the example of Lotus, it was utilized in a more structural application as a result of the geometry that was applied to that alloy. Now this alloy, 6060, and we see some overlap in a 6005A and a 6063, tend to be alloys that can be quenched with the utilization of air only. So the result of that is tighter tolerances, less twists, less bow, which result in better downstream assembly, welding, and fabrication. When we rise in silicon and magnesium, we get into a 6005A, some overlap in 6082, an overlap of 63, and an overlap of 61. We typically see these alloys utilized in auto chassis, structural, solar racking type systems, structural integrity. This band of alloys can be quenched either by air, an air-water mixture, or a full water wall quench. Again, this band of alloys is increasing relative to the percent mag and percent silicon. Then we get into the 6082, 61, higher band of 6005A, which is typically utilized for auto intrusion beams, bumper beams, auto chassis, and structural application. Typically full water, highly sensitive alloys to quench rate. So as we go up in silicon and mag, we gain mechanical properties. The process within the extrusion system changes as a result of quench, and we get an increase in strength, but also an increase in cost. So this is a nice breakdown to see how the difference in silicon and mag are represented within a given alloy. So a little bit about chemistry, and now we'll talk a little bit about microstructure and processing. Considerations for microstructure. There are many considerations for microstructure: grain size, grain geometry, grain structure, second phase particles. It's a fairly long list. Microstructure affects our mechanical properties, formability, our corrosion resistance, weldability, and fracture resistance. Microstructure depends on the alloy composition and the extrusion process itself. A little bit about grain microstructure. We're going to talk basically about three here today. Recrystallize grain, which is the most frequent type. Grain sizes range between 25 and 400 microns in that range. And the key here is the max grain size should be controlled for formability. A fibrous grain, typically higher strength alloys with specific alloying elements, increased mechanical properties, increased fracture resistance. It includes a better resistance to corrosion as a result of the fibrous grain itself, but a reduced ductility. Then we have a mixed grain structure, which is a fibrous grain typically with a recrystallized layer represented here. Fully fibrous grain may not be achievable. The surface recrystallizes first, and that's represented here in the image. Recrystallized layer thickness needs to be specified. Ductility and mechanical properties may be impacted if the recrystallized layer is too thick or the grain size is too large. So we're monitoring the grain size of the recrystallized layer as well as the band thickness of that layer itself. To go further in the webinar, we're going to talk more about the mixed grain structure, the fibrous recrystallized. So mixed grain structure, how can it be specified? There's many different ways to go about that. My experience has been the total thickness of the outer layer typically has a percent not to exceed. That percent could range by specification or by requirement, but for example, it may range from 10 to 20% or 25%, depending on the application, the performance requirement. But considerations that have to be taken into effect is the seam weld location. So in a porthole extrusion application where seam welds exist, typically these specifications don't apply in those areas. They typically don't apply in flanges, and wall thickness needs to be taken into consideration when those specs are applied. How is fibrous grain achieved? What manufacturing parameters are impacted? You'll see here primarily a lot of it has to do with time and temperature, but chemistry, as we spoke before, of our raw material, the homogenization process and cycle associated with that raw material that's provided to the extrusion press, the billet temp and length itself, so the temperature of the raw material that is loaded into the extrusion press is critical, the temperature of the tooling, the container temp in which the billet resides during the extrusion process itself, the speed in which the extrusion occurs, die design and metal flow, the quench rate, profile geometry, and extrusion ratio. So a lot of process parameters are involved in the creation of a fibrous grain. So let's look at the process. Just a brief primer. The strength of 6000 series in general comes from magnesium and silicon combined to make Mg2Si. Achieving consistent properties requires a very fine Mg2Si precipitates distributed well throughout the product. How do we achieve that? Achieving desired properties is heavily dependent on three processes that exist within the extrusion operation. And here we represent the general stream of an extrusion process. We have an oven, we have an extrusion press with a quench box right after the press, a cut down saw, the stretching application, another saw that cuts down to lineals, in our age oven. So the first stage that's most critical proper metal temperature through the die is required to put alloying elements into solution. So our raw material that's being supplied to our oven, that's in line with the extrusion press, has already had the homogenization cycle. So at this point, we are trying to achieve our proper billet temperature that is being applied within the extrusion press. So that's a key aspect of it. Second part is proper cooling and quenching after the press. This is required to trap the mag silicon in solution while avoiding distortion. So the objective of this, and this is a key factor in the extrusion process and what drives a lot of cost, what drives a lot of tolerances associated with product, and has a big impact in the alloys, specific alloys that are achieved relative to the performance need. But the objective here is to quench fast enough to avoid undesirable concentration of alloying elements and achieve desired hardness, yet slow enough to minimize residual stresses and distortion. Okay, so right after the extrusion press, we took a billet, we brought it to the appropriate temperature, we took into consideration the die design and the metal flow that goes through the press, we extruded at the proper rate. Now we must quench that product. And the graph that we showed earlier that was relative to the mag and silicon represented really three different layers. 60, 60, 63, this process here can be achieved by an air quench. So the distortion of the product is much less. As a result of the reduced amount of distortion, recovery rates are higher, downstream tolerances associated with profile cross-section, twist and bow are improved. As a result of the lower mag and silicon, the production rates are also higher as a result of the improved metal flow through the extrusion. So a 60-60, a 60-63 low mag, low silicon alloy would flow out of the press here at step 2 through an air quench and achieve the proper mechanical properties in T4 condition. Now with a 6005A or a 6061 or a lighter wall 6082, that requires a more aggressive quench rate. So now we must introduce, in addition to air, we must also introduce water, and this is called an air-water mist. So more distortion relative to our 60, 60, 63 low mag silicon alloys, but less distortion than a full water wall quench of a 6082. Okay. Then our third band of alloys, which is the higher the mag silicon, which would be represented as an example of that would be a 6082 alloy. That requires a very aggressive quench rate. So immediately exiting the extrusion press, and let's say that exit temperature is 940 degrees Fahrenheit, we must reduce that material properties temperature, or reduce the material's temperature. And that is in the way of a full water wall. So you can imagine an extrusion that is 1,000 degrees Fahrenheit within a 20 or 30 foot length being reduced down to maybe 100 degrees Fahrenheit, the amount of distortion and twist that can occur. Also, as we mentioned with the 6082, it's a higher mag silicon alloy, so the production rate is reduced as a result of the material flow through the extrusion die. But the quench process here is critical for the microstructure, it's also critical for tolerance, and it's also critical for performance, productivity. So here is a graph that typically is used by extruders in the understanding of the quench rates. I show this just for reference. This shows time represented here in the horizontal versus temperature, and the difference in the quench rate requirement of a 6061 alloy versus the quench rate and time relative to a 6063, just for an example. The third critical part of the process is proper aging required to grow and disperse the precipitates. And those age ovens, while in the same location as the extrusion operation, are offline from that operation. So temper, artificially aging extrusions at raised temperature for a period of time will increase strength for various alloys. A lot of the tweaking can occur during the age practice, and age practices can range from 5 hours to let's just say for discussion purposes 12 hours for a 6000 series alloy. Typical extrusion tempers are F, extruded and air cooled, O, fully annealed, H112, strain hardened, used for non-heat treatable alloys. T1 is cooled from an elevated temperature and naturally aged. T4 is solution heat treated and naturally aged. So we get a T4 condition once we exit the extrusion press and maintain our quench rate, whether it be air, water, mist, or water. T5 is cooled from an elevated temperature and artificially aged. T6 is a solution heat treated and artificially aged temper. And T7 also solution heat treated and over aged application of a temper for stability reasons. So aging and temper is critical and can add additional performance properties to your extrusion. Okay, so we talked a little bit about geometry, a little bit about chemistry and microstructure, extrusion properties and performance, and how they were achieved. Now here's a case example of an extrusion. Typically, a print could come in like this, looks relatively simple, not a lot of tolerance applied to it, very simple alloy applied, typical 60-63. However, the application may be structural. Could be a bumper, it could be a structural member. So the questions that come when you see a print like that and what needs to be taken in consideration and specified for the extrusion are represented here, and the list is probably 3 times as what I've shown here. But here's some consideration. Weld line locations, and what are those requirements? And was FEA done? So for example, is it okay to have a weld line within these vertical webs? Or is there stress risers relative to the outside of the product? Or will this product be bent in such a way or crushed where the weld needs to be applied in certain areas? That needs to be understood. Post-weld locations. Is there post-welding associated with this product? If so, we may not want a weld location where the post-weld actually starts and finishes. What is the post-manufacturing? What needs to be taken into consideration? How much machining will occur? There can be adjustments made in the mechanical properties and the microstructure associated with for machining. Is grain size a concern? Recrystallization layer, as we talked about before. When we start specifying these items, and is there an IGC specification requirement? It starts to determine the alloy and it starts to determine the quench rate. And once that's understood, then we need to start to understand what are the tolerance requirements. And based on that alloy and based on that quench rate, do we need to apply tighter controls relative to the dimensions and also take into consideration twist and bow? As we talked earlier, based on those alloys and based on that mag silicon content, it's going to determine the quench rate required, which will ultimately have a better understanding of what the twist and bow is. Another key aspect is yield band. Is there a yield band that's required? If the performance requirements of this beam here specifically have such a specification that the yield needs to be controlled within a band, what is that band? And what chemistry would be required and what process parameters would need to be in place to hold a band and how tight of a band. So when we're presented a cross-sectional drawing like this, these are the questions that are sometimes missed. And these are the opportunities to add value within that extrusion. The best time to provide value in an aluminum extrusion is at the time it goes through the extrusion die itself. So the more understanding of these parameters, the more value that can be built into the profile. So here's some just adjustments based on what we talked about. We went through a 60-61 alloy versus a 63. We put some controls relative to straightness and twist because now it's going to go through a water wall, so that needs to be taken into consideration. Tolerances, unless specified otherwise, were changed to a precision AA. We noted our runout surfaces so that we understand if there is any graphite marks from the runout, they're on a non-welded surface. We specify our mechanical properties with a specific yield strength. So we applied a band, specified the requirements relative to the balance of the mechanical properties, and put a specification on a recrystallized layer. We also noted in this application that no die welds could be applied in this area as a result of the performance need of the extrusion. Again, a 60-61 alloy with these mechanical properties requires a full water wall quench. So we also apply a flatness spec across the bottom for any distortion, a parallelism represented here, and a perpendicularity to hold the squareness of this extrusion as it goes through the quench process, the full water wall quench. So the results of those modifications: a tighter yield band was able to provide a better predictive performance. Specified grain structure and performance yielded better fracture resistance, better manufacturability, repeatability, and reduced cost. As a result of sectional controls and understanding of the twist and bow, tighter geometry control, squareness, twist bow, etc., considering the quench that was utilized for this specific alloy. The understanding of post-weld locations and surface conditions and seam weld were taken into account for downstream operations. And engineered weld locations relative to high stress conditions were taken into account. So in conclusion, North American extruders are committed to supporting the effective use of extrusions for the automotive lightweighting. An active automotive team within the AEC exists, extruders with extensive programs, TF certifications, and robust engineering resources supported by metal suppliers are here to support the automotive industry and support the lightweighting challenges that are being presented. Substantial capacity commitments are being made by extruders. Capacity is growing, and the capacity of extruders with the capabilities of supplying automotive product is increasing as well. And knowledgeable technical resources are here to help you achieve the desired performance. My recommendation, the AEC's recommendation, is to get a qualified extruder involved early. A qualified extruder can help with the guidance of the chemistries required. They can help with the tolerance applications to better control relative to the specifications that are required and help meet the performance need. Represented here are AEC auto team members that are involved. This group works very closely together, and this group represents our automotive team with the AEC. To find an additional extruder, you can go to AEC's website at aec.org and choose the pull-down menu that says Find a Member. I know that we ran just a little bit longer than expected, but I'd be open to any questions, or you have my email address here. It's mbutterfield@magnode.com. If you would like to send me any questions, I would be glad to to answer myself, or if it's a question that I can't answer, I'll certainly get that question answered for you. So thank you.
Thank you, Mark. We certainly appreciate that. Once again, this is Joe Steele from LIFT, and we have been recording this presentation. It'll be available on our website at lift.technology. If you click on the technology tab, there's a LIFT Off webinar page, so you can review this presentation as well as others that we have had in the past. However, there were a couple of questions that came in. Mark, hopefully you can answer them, or you can be contacted offline here. I see you have your email address and phone number attached. But the first question that came in was, what is the elongation difference between the 6061 and 6063 with the slight change in the chemistry? I know this goes back to earlier in your presentation when you were talking about the differences, but if there's a elongation difference in those two, can you let us know?
Yeah, there is a difference. The 6063 and 6060 elongation is relative to thickness. So the 6061 minimum elongation is at 8%, where 6063 and 6060 can be at 10%. And chemistry adjustments can be made to affect that elongation percentage.
All right, thank you. And another one, can you comment on the impact of the quenching and stretching on the physical properties that we're dealing with, and how are these processes tuned for the various, grades, 6063 and 6082, et cetera?
Yeah, so when in the quenching process, there's a lot of critical parameters associated with that. So the exit temperature there's a parameter associated with the exit temperature, and that's relevant to the alloy and the geometry itself. So exit temperature is key. The exit temperature also becomes the entry temperature into the quench media. So that's critical in the mechanical properties that are achieved, and then the rate in which the temperature is dropped. So the critical quench rate is key as well. In a typical extrusion process, you'll typically see an infrared temperature monitor that will capture the exit temperature, the quench entry temperature, and the exit temperature out of quench, which would ultimately give you that quench rate. The stability and consistency of that aids in the mechanical properties themselves, and those are key process parameters when a yield band, specific yield band, is applied.
Thank you. We have a question here that might, I don't know if this may need to go offline or not, but does AEC have a list of heat treaters that can heat treat and water quench long, 12-foot length extrusions in a manner that minimize distortion?
Yeah, what I would suggest in that regards is to contact the AEC or look through the AEC's website, aec.org, or contact the AEC directly, and they can provide some guidance relative to who may have those capabilities in the industry.
Okay. Is there an industry specification like ANSI H35.2 that is used for dimensional tolerance descriptions?
Yeah, there's an aluminum association tolerances relative to extrusion. It's aluminum standards and data that you can go to relative to the tolerances associated with the cross-sectional extrusions and also twist and bow.
Excellent. Again, if you have questions, please use the GoToMeeting taskbar and address the questions to the organizer, and then we'll continue on here. We have a few more minutes. Do some of the AEC members specialize in certain alloys, certain aluminum alloys, like 1100 or 1050?
Each extruder has an alloy that they may specialize in. As we mentioned in the presentation, 6000 series is pretty broad. Most extruders can provide a 6000 series alloy. Some extruders can provide a 1000 series, 3000 series, and some extruders specialize in 7000 series. Each of those alloys while they're extruded in a typical process, they have different process parameters that are required. So, for example, a 7000 series extrusion, while it may be utilized in the same equipment, the processes associated with it are slightly different.
Have you used any software such as HyperExtrude from Altair or Thermocalc to simulate the extrusion process and changes in microstructure during the aging and quenching?
We have not. There is software, as you've mentioned, that's out there for simulation, but Magnode itself has not had experience with that.
All right. Is there an increased, or what is the increased discard rate due to the quench distortion when you go from 6060 to 6082?
So that is relevant. So each extruder, the position in a 6082 alloy, the location of the quench box relative to the extrusion press helps determine how much scrap is incurred. So, for example, during an extrusion, the extruding of a billet, any material that does not go through the quench box during the extrusion cycle itself must be scrapped. So the distance, any material from the die face to the water wall itself during the dead cycle must be scrapped. So that increases the percent scrap relative to 6082. And that's specific to each extruder and their location of their quench box. Now 6082, pending the profile, the mass balance or imbalance, and the complexity of the cross-sectional geometry and the tolerances required for twist and bow, typically give you an understanding of what that scrap rate may be. Just for general discussion, on a typical part, if the geometry was the same, with maybe half standard twist and bow, to go from a 6082 maybe to a 6063 air quench, it could represent a 5 to 10% reduction in the recovery from the system. That's just a broad statement.
All right. Again, if you have a question, we have a few more minutes left. I want to be respectful of everyone's time. And again, you can contact Mark offline with his email address and phone number that are on the screen. And again, this presentation is being recorded and will be posted on our website at lift.technology by early next week. If you go under the technology tab and click on the Lift Off webinar series page, you'll be able to review this one as well as some of the others that we have done in the past. I don't know that I have any more questions coming in, so with that, I will give everyone back a few minutes left in their day. And I want to thank Mark and thank Lynn at the AEC for participating today. Thank everyone for joining. We are here every third Thursday of the month at noon Eastern time, so stay tuned to your emails and look on our website for upcoming speakers. And if you have interest, please reach out to us to become a speaker as well. So thank you very much. And with that, we'll sign off for this month. Thank you, everyone.